All right, hey everyone, let's go ahead and get started. Last we left off, we were talking about some vector properties. We ended on doing some cross products of a few vectors. We've seen that a little bit with finding the torque of something that's rotating. Remember that torque is sort of the analog for it's the rotational force. Torque is a spinning force or a turning force. So we have this way to express force in a system that rotates. Let's move on to something that we've done in the linear sense, which was linear momentum. We're going to move on to angular momentum. Okay, so for the linear case, we had, let me change, that's one thing I forgot to change the color. We had linear momentum, which was just expressed as P equals mass times velocity. Okay, so we have P equals mass times velocity. Remember, that's momentum was a vector and velocity itself is a vector. In this case, it's linear velocity. Momentum, also you could think of as just how easy can this mass change velocity. Something with a lot of momentum is it's either a large object moving slowly, or it's related to the size of the object, the mass of the object, and its velocity. So my example I brought up in the previous lectures was compare a semi truck starting from a stoplight. It takes a lot of effort to get it to start to move, versus someone on a bicycle. There's a small amount of mass. They're able to start and stop much easier than this sort of semi truck. That's an object's linear momentum. Let's talk about angular momentum. There's a similar thing for things that rotate. Something that spins has this is it's a law of inertia for spinning. Things just want to stay the way they are. So things have a way of measuring how easy they are to start and stop spinning. This is angular momentum, which is denoted with capital L. This is also a vector. It has a specific direction. And for our purposes, we're going to use L is the radius from, say it's a point mass spinning around a pivot point. So how far away is it from that pivot point? We're going to do a cross product with its tangential momentum. So at every moment, we do this, at every moment, something orbits around or revolves around this point. There's an instant where there is a tangential momentum, and it will be pointing in a different direction for something that rotates. This is how we can relate angular momentum to linear momentum. Does that mean it's the one we can always use? Maybe not. Maybe we're not given a linear momentum to begin with. Let's see how we can massage or modify this equation a bit. Let's have a little graph or a little picture to go along with this. Here we have let me draw this picture first, and then we'll sort of do the calculations on the left. So this is a grid of the X. Let's try to make this coherent. This is X, Y, Z. And on this sort of grid, I didn't draw the whole thing, so I wanted to make it clear what I was pointing at. On this sort of axis, there's a object rotating around, rotating with its axis as the z-axis. So let me try to draw that. I didn't prepare that. So nope, something like that. That's a lot better. Okay. So we have just an object in the XY plane going in this pattern, or having this motion, this rotating motion. Now it can be a ball, sort of a mass, it's on a rod of a specific length, or this can be just a disc itself that's that's rotating. Whatever the case may be. For this example, we'll say it's just a mass, and it's a specific distance away from the pivot point. That's this R. Things that rotate, we're going to be making a circular path. So it's a radius R. And for our equation up here, maybe we are given the linear momentum. And in this specific instant, let's say this object is making a path like this and is going around that way. So it's sort of flat on the floor here. And at this very instant, it is traveling with a momentum pointing that way. All right. Let's put this equation over here. L equals R cross P. Now, all of these are vectors. And I guess I can move on to the next step I was going to do. R cross mass times velocity. Velocity was the vector. If I sort of break down momentum, what that was, it was the mass of the object and its velocity. All right. Last time when we were doing cross products, I was talking about the right-hand rule. What would be the angular momentum, the direction here of the angular momentum of this example picture? Well, whatever's first in this order, that's where I'm going to point my fingers. So all of my fingers, I have a flat hand. I'm going to point them that way. So in this case, for the picture, it's R sort of angled toward me a bit. And then I'm going to curl my fingers in the direction of the second term. So I'm going to initially point with the first one and then curl in the direction of the second variable. In this case, it's going like that, and I'm curling like that. So the way my thumb points is the result of this cross product. So that would be the direction of the angular momentum. In this case, the angular momentum is pointing directly up. Try to do that like that. All right. Well, what if the the object is changing? It's always rotating. Is the angular momentum direction changing as well? Let's see. So here we have it on the plane. Here's the origin. Let's say instead of having the object right here, let's follow it along and let's see where the angular momentum is pointing when the object reaches right here. So we have a radius or an R like that. And at this specific moment, the this point mass has a momentum pointing that way. So R cross, so let me try to R cross P, my thumb is still pointing directly up. And it's directly up because all of these cross products I'm doing are on the same axis as the origin here. So even in this second case I've done, well, angular momentum's still pointing up. So hopefully that'll make this second step a bit more transparent. I'm going to take this cross product term. I'm going to say anything that is, I'm going to say this is just, I think I've also defined this before in the last lecture. The cross product can be seen as just the sine of the different angles of the two in the cross product. So that's R M V, so that's all of these, but then sine of 90 degrees. And that's specifically in the, this is giving it a new direction, K hat. So that's typically attributed to the z-axis. So that's saying this angular momentum is pointing in the z-axis, or pointing the positive z direction. Okay, sine of 90, that's just 1. R M V, and it's pointing in a positive z or in the k hat direction, up. Let's take this sort of where are we going with this? Why am I doing this? Well, I want to show how maybe we're not always given things in tangential terms. Maybe we're not given a tangential velocity v. Maybe something's already been made a little easier for us. Maybe we know the moments of inertia of this object. So how can we turn this velocity into something angular? Let's turn it to the angular velocity. Turning it into an angular velocity will give us Rm, let's go like this. I'm going to rearrange m r squared omega, still in the k hat direction. And let's take this omega and k hats that's saying a velocity or a speed. There's no arrow on top of this yet. So this is a speed and a direction. That means that the velocity is also saying it's pointing up like that. So by combining these two, we have this new term, and ultimately we may see that this is familiar. If we have r squared omega, that is just, if we have mr squared, we have the moment of inertia. So angular momentum is also represented with the mass of the object, the distance the object is rotating from a pivot point, times its angular velocity. And if we don't have, or maybe we're given something slightly different or slightly prepared for us, we might be able to say angular momentum is the moment of inertia of an object times its angular velocity. So we have these, we have a few ways. So we have this up here and these down here. We have a few ways of expressing angular momentum. Let me take this picture example and let me sort of demonstrate that it might not always be as straightforward as it seems. So I'm not going to, you see with this picture, I didn't really have any values I added. But let me sort of make this apparent that it can get complicated. So for this image above, we have Z, we have X axis, Y axis, and there we go. You see this path that I traced for this particle, this mass right here. It is in the same plane as the axis of its pivot point, of how it rotates. What if it is not in line with its pivot point? What if it is off center and it's rotating away from the pivot point? What I mean by this, so imagine this is this is like a plate sitting on a table, and imagine lifting the plate up. And so it is up here. Let me try to draw it. The same sort of size. That's pretty good. Anyway. So we have this new path. And I'm going to, instead of having it right here, I'm going to, let's just look at the angular momentum of the object when it's right here. It's still moving in the same sort of path. This is counterclockwise as seen from above. So I'm going to try to go that way. Okay, so it's angular momentum. Let's try to show that. Well, what is the radius from its axis of rotation? Well, it's still on the origin down here. So instead of being that straight horizontal line, it's going to be something like this. So there's R, and its momentum, it's still a flat path. It's still pointing that same direction. That way. And now let's do the cross product of this. So R, now it's at a new obscure angle, RP. The angular momentum of this is not directly up, it is shifted. It's shifted over that way. So maybe if you can picture this system in your head, maybe if you see that this is, or you imagine this is a pole and a mass, and you try to rotate something like this around this pivot point right here. If you're experienced with, you know, devices in the real world, you might notice this thing can sort of begin to wobble and shake. And this is the premise for like something off center in your washing machine, beginning to have this momentum, this angular momentum, creating something that's might begin to rock and shake violently. Because this momentum is pointing this way, it's pointing that way at this specific moment. But let's say, for example, I'm going to erase this next little example. Let's say we follow it around over here, and the momentum is pointing sort of at us, and the radius is that way. So let's do this cross product. RP, the momentum is that way. You see the angular momentum swivels around with this off-center mass. So the momentum is constantly changing. There's this sort of rocking feel to it. I'm going to erase all of this because it just makes my picture a little too messy to make sense later if you're just looking at the picture. Okay. So we have a nice way of finding angular momentum. Let's do a little example. All right. A 1,200 kilogram car moves counterclockwise on the XY plane, as seen from above, in a circle, a radius of 20 meters with a speed of 15 meters per second. We want to find the angular momentum about the origin. Okay, let's do it. So I'm just going to do a real simple picture. It's just an object that's traveling in a circle. Let's put it right here. Around a fixed axis, or it's a circle, so it's maintaining a constant radius. R, constant radius R. Try to make that visible. Okay. It has a mass and it has a specific linear velocity or a linear speed. That's why they call it speed right here. We know it's sort of tangential because they give it this value as meters per second. So it's pointing something like that at that specific instant. Okay. Starting from the top, angular momentum is r cross p, radius cross momentum. Since we have tangential velocity, we can use r mv, and we can use sine of 90 degrees, k hat. And we don't always have to do this every time. Knowing that it's on the plane of the same, it's on the same plane of the axis that's rotating around. So we're going to say it is just r mv k hat. And actually, I need to save some space. So I'm just going to fill in what we have. 20 meters, 1,200 kilograms, and 15 meters per second. And the angular momentum will be pointing in the k hat direction. This turns out to be 3.6 times 10 to the 5th kilograms times meters squared per second. And it is pointing in the k hat direction. So that is the angular momentum of this system. And that's part A. Let's do part B. A 1,200 kilogram car moves in a straight line past the origin at a velocity of negative 15 meters per second in the I hat direction at a distance y equals y naught. It's 20 meters away. So it's a constant 20 meters, so it's a straight line parallel to the x-axis. All right, let's do this one. Quick picture. We have something like this. So we have x, negative y pointing sort of back into the picture. Oop. Positive y is pointing out this way. And there's z up there, similar to z being up there on that picture. And it's just a car moving past the origin. So it's moving that way, back there. Let me make it a bit more in the picture like that. In a straight line. Okay, has a mass, has a velocity, and it is a specific distance away from this origin. So from the origin to that point, that is a radius. Even though it's not moving in a circular path, the question is just asking, what is the angular momentum if this were to start rotating from its current trajectory? Okay, so we have radius, mass, velocity. The problem is this thing is moving in Cartesian coordinates, and what we have, we want to use, well, since it is moving in Cartesian coordinates, we can use the cross product a little easier than normal. So first we need to define what the components are. For R, we have just initially, we will always say it's X I hat plus Y J hat plus Z K hat. Now let's put in the values that we actually have for our system. We have something moving at a constant X value. It's a constant horizontal velocity, X I hat. We have this thing moving. It is a specific distance away, J hat, and Y naught. That is 0, because there's no motion up and down in this plane. For the momentum, it's mass times velocity, and we're given the velocity. It's moving. This is where it's moving in the minus mv I hat direction. All right. I guess technically this would be 0 also. But we'll leave that because it's going to cancel 0 from this other step. All right, so we have angular momentum is R cross P, which is just X I hat plus Y J hat cross minus MV I hat. Let's do this cross product. We gotta cross the directions of these vectors. So we have XMV I cross I minus Y naught MV J cross I hat, J hat cross I hat. And you can see right here, cross product with itself makes this term go to 0. J hat cross I hat turns into negative K hat. So we have negative Y naught MV negative K hat. And that just turns into Y naught MV in the K hat direction. Now look what we have here. We have a distance away, which is constant. We have a mass, and we have a tangential velocity. It's the same thing. Let's go. It's the same thing as we had up here. Distance away, mass, velocity, tangential velocity. So we have L angular momentum is equal to 20 meters. It's 1,200 kilograms. It's 15 meters per second. And it's in a positive K hat direction. This is the same exact operation. We have 3.6 times 10 to the 5th times 10 to the 5th kilograms times meters squared per second in the k hat direction. All right, that's fine. We have enough room. Same exact thing as the first part. Whether something's moving in a straight line directly past a point of reference, or if something is moving in a constant circular path. If we take a picture, if we just take a snapshot at any moments, they both look the same. When object is moving a specific tangential direction, a distance away from the pivot point. Same thing with a rotating object. Take a picture, the object out here is moving at that direction, specific radius away. So they'll both have the same angular momentum. Let's look at question, or I guess part C. We don't have this car anymore moving in a specific pattern. We have a uniform disk in the XY plane with a radius of 20 meters and a mass of 1,200 kilograms. And it rotates counterclockwise at 0.75 radians per second about its axis. So what we're saying, we're kind of imagining, is what if we took that mass, that point mass, and we sort of smushed it out into the shape of a disk, and we rotated that disk. What's the angular momentum of that then? So let's find out. So we have simple picture. We have now we have an actual disk that is rotating. About some axis in the center. So we have L. I could say L equals R cross P, but I don't have any information that would make that useful. Let's go back to the problem. So uniform disk, have a radius, I have a mass, I have a, what is this? This is a angular velocity. Okay. Since it's already been converted to an angular velocity, and since this is a disk, I already know, from a chart somewhere. I made a chart earlier, it's a couple pages back on my notes. The moment of inertia of this simple shape is easy and already known. And I also know that angular momentum is I omega. So moment of inertia times angular velocity. And we have I omega. Let's say it's not a vector. We strip away that vector sign and we just say it's pointing in the k hat direction. And this is where we insert what we know as the angular, or sorry, as the moment of inertia of a disk. We can find that easily from a chart. It's 1/2 mr squared omega in the k hat direction. And that's where we can just place in the values we're given. All right. 1,200 kilogram disc has a radius of 20 meters, and it's rotating at a specific speed, 75 radians per second. What we're given doesn't equate to the same amount of angular momentum, though. What we have is 1.8 times 10 to the 5th kilograms times meters squared over seconds, pointing in the k-hat direction. Why is it different? Well, first thing we could check, we could see we were given a different velocity to start out with. We're given an angular velocity. We could check to see if that's the same as this tangential velocity up here. Okay. Something that we might take a note of is for the previous problems, we were looking at a point mass. It was a solid object with all of its mass in one point, and it was rotating around a pivot. All of its mass was here. In this specific example, in part C, the mass is no longer located at that specific, it's not all clustered together at that point. It's spread out over the entire disk. So there's less mass at that specific point because it's been, distributed everywhere else. That can contribute to a smaller angular momentum. Okay. So we have that, and then I have that and that. All right. Next up, just some extra stuff for angular momentum. Some additional key points. In general, if an object is spinning, it has angular momentum. Sort of doesn't want to change its current state. In order to change its state, you're going to need to force it to spin more. And what is the spinning force? That's torque. So there's a specific relation, and it seems sort of straightforward, but it's always good to write this down for your own reference. What this says is the net external torque about a fixed point acting on a system equals the rate of change of the angular momentum of the system about the same point. The equation looks like this. Over change in time. Okay. What is this saying? It's a whole lot of jargon. You could get lost pretty easily. Let me simplify it to just a few words. This is saying that the force you add, force added, is proportional. I'm just going to do that, proportional to the change in momentum. So torque is a turning force. momentum, it just, if you're having trouble with, picturing things rotating, always think back to the linear case. If something's moving out in space in a straight line. It's not acted on by any forces. It's going to continue to move in that fashion with that specific velocity, and it'll have that same momentum. And it's not until you force it, you push this, box floating out in space, not until you push it, that it will get more momentum, or maybe slow down, get less momentum. That's the same thing that happens with things that rotate. It's not until you force it more that they will gain or lose angular momentum. So force added is proportional to the change in your momentum. I could take this concept and go a little further and talk about, the impulse, and go into what were we in linear momentum. We talked about collisions, maybe two things collided and momentum was transferred. Well, you can also have some sort of transfer of angular momentum between objects. I'll just write this down, but we're not going to be examining this a bit in detail. But the property still holds. So angular momentum of a system, T1, T2, net external, dt. So this is like, think of it like you have some sort of thing spinning, and you give it a short, quick burst of more spinning energy. This is a sort of a impulse of torque, quick and strong turning force. This is sort of this impulse of angular momentum. After this, we could talk a little bit about maybe a system has something that is both rotating and spinning. What do I mean? Well, let's look at a everyday example. The solar system. In the solar system, I just did one planet. There are several planets and dozens of other classifications of objects like dwarf planets, comets, asteroids, all moving around the sun, or rotating or orbiting around the sun. In this case, sort of modeling just Earth. We have this planet that is moving on this path around with a specific tangential velocity relative to its center of mass. And it's a specific distance away from the pivoting object, or in this case, the sun. But this object, this small object itself, is also spinning. So when the Earth spins, that's just a day for us. One time when when it takes Earth to spin once, one completes spin, that's 1 day on Earth. So let me try to go like that. So there's a combination of angular momentums here. There is this large outer angular momentum caused by the orbit. So the direction of uh, this R right here, so R and the direction of its path in the orbit, R cross V, it is directly up in relation to this plane. So however, there's also, since this planet is spinning, it has its own angular momentum of this spinning action, which points in this way, in this direction. You see, this becomes a nightmare when then you consider I just did one planet orbiting and spinning around central star. For our solar system, it's fairly average, maybe a little small. There's many, many, many things all contributing to this angular momentum. For this case, we have the angular momentum of the system is equal to just the sum of all of its individual components. And in this case, for the orbits, it's pretty much the same equation. I'm just specifying that it is the mass of the planets and the tangential velocity that I drew right here. All right. We have that. We have this torque and angular momentum on the z-axis. This is pretty much sort of a summary of what we've done before up to this point. So let me write torque in relation of a cross product, sort of. Torque is directed in the z-axis direction, or I guess, yeah, I'll just say t z is equal to r distance away, and it's just a force applied in the xy direction. And then I've been talking about angular momentum today. And momentum in the xy plane. All right, so those are sort of the base relations that you can always come back to. I think I have one more page. All right. Your book likes to sort of end their chapters on like a final definition. So we have conservation of angular momentum. So the grand finale, wrapping up all of the things that we've just covered. What we have is sort of this little explanation. If the net external torque acting on a system about some point is 0, the total angular momentum of the system about that point remains constant. This sort of is a callback to that it's similar statement I said about torque and momentum. Just write it real large. Net external is equal to L, the system. So if the torque is 0, then the angular momentum of the system is constant. Similar to what I've said just a while ago, if there is no external force, we have this object spinning. We have this water bottle spinning at a constant speed. Again, always imagine this as frictionless, perfect. Once it starts rotating, it'll rotate with that constant speed until acted on by an external force. In this case, an external turning force is a torque. So if this object rotates and is not acted on, that's what this thing is not acted on by some sort of other turning force, then the momentum of the system is constant. It's constant throughout however it is arranged. If you spread the thing apart or move it closer together, the momentum of that system is constant. Let's do a little example of this concept. So we have 2 point masses, M1 and M2, of 2 kilograms and 5 kilograms. They rotate about a central point. Their distance away, R1 is 10 meters, R2 is also 10 meters. Counterclockwise when seen from above. The first mass slides closer to the pivot point, to a distance, to a new distance, so R1 prime of 3 meters. I think I can add in here. Let me add real quick in here. So what we want to do is find, that's the one, go like that. What is the distance from the pivot? What distance from the pivot is M2 pushed to? What do I mean by pushed? I had a hard time phrasing this. If the angular momentum that we can see is constant, what is the new position of M2 after this action? So let me also add in here to this question. I'm going to say, assume total angular velocity is constant. Okay. So we have this system where no external torque is added, okay? So I can say that the angular momentum of the system is constant. We have 2 point masses that are just some distance away from this pivot point. So imagine like planets orbiting around the sun. That's sort of a decent representation. The planets themselves are minuscule compared to the size of the sun, but these are just like point masses that orbit around some pivot point. The total angular momentum of the system is conserved. It's constant throughout. So angular momentum of a final scenario is equal to the angular momentum of an initial scenario. Wherever I want to take 2 snapshots, the angular momentum of these 2 pictures are going to be the same. Since these are just point masses, some distance away from a pivot point, I'm going to use the form L is I omega. They're just 2 point masses some distance away. Why am I using this form? It's because, well, I haven't been given any tangential velocities that can help me determine maybe like an angular velocity. Well, they have said that the total angular velocity is constant. So let's write this out a little bit. So we have the total moment of inertia of the system, the final, times the angular velocity final is equal to the total moment of inertia initial times angular velocity initial. Said it's constant throughout. So that means that's velocity final equals velocity initial. So I can pretty much just cancel these 2 terms out. Or, just cancel them like that. We'll say that the problem has reduced this to just saying the moments of inertia are the same before and after. All right. Now that we have this, we can find the moment of inertia of the system before. We can find the moment of inertia of the system after. Shrink this down a bit. All right. So the initial case, that is m1r1 squared plus m2r2 squared. So this is just like moment of inertia 1, moment of inertia of the second object. That will be 2 kilograms times 10 meters squared plus 5 kilograms times 10 meters squared equals 700 kilograms times meters squared. For the final case, m1 r1 squared. And let me make this sort of look different by making that prime. Plus m2 r2 prime squared. All right. So we have this, they haven't changed mass, so there's still the same mass after one object sort of slides in a little bit closer. But now it's, let's see, where is it? R1 prime equals 3 meters. This is still the same mass, except now it's R2 prime squared. Okay. We have 700 kilograms. So we have, I'm going to arrange it like this. So I'll say 700 kilograms times meter squared is equal to 18 kilograms times meter squared plus 5 kilograms R2 prime squared. This will turn into, we have all of the values. We can solve for R2 prime. R2 prime is 11.7 meters. So this is a very basic problem, but it shows how a system may act. This is something we see when we have done some sort of deep space observations. This is an actual thing that happens. Imagine in a gas nebula when there's a star formation. Gases will mix. Eventually, gravity will crush the various gases down into a single point, creating a fusion reaction. This star core is created. Now, as these, as a lot of this mass moves closer towards this pivot point, they begin to speed up as they move in towards the pivot point. But then there's some gas on the outside that doesn't get drawn in right away. As it moves in, some of the gas moves out because the total angular momentum is conserved. So let's say in general, the gas cloud was sort of just spinning a bit. As some of the gas moves in, a lot of the other gas is pushed outward. That's sort of why there are these creation of planets on the outside sort of rim around a star. That's why all of the gas around a planet, around a star, doesn't just immediately get sucked in all right away. So if all the gas got sucked in all right away, there'd be pretty much no planets. We have some of the gas coming in, creating a star. The remaining gas gets pushed out and forms together, creates other elements, and it doesn't create other elements. It sort of clumps together in other various ways. So we have this conservation of angular momentum popping up in the deepest reaches of space. I have let's see. I have a small example of torque and angular momentum with a little gyroscope here. Sort of off topic from the space discussion I just had, but in this chapter, it does cover somewhat gyroscopic motion. Let me quickly, maybe I can make a little demonstration for, let me get this set for this. Okay. After this is pretty much the end of the chapter. Next chapter I'm going to move on to is fluids. It will be pretty short, pretty good. Let's go. Maybe I can manage to do this. All right. So we have gyroscope here. It is a object that spins fairly well. I've noticed there's some friction in this sort of the bearings here. But as this object, this disc or this ring spins around this axis, there is a force that's being applied. Now, if I were to hold out the gyroscope like this and let it go, it's going to tip downward like that because there's a constant, there's a force on this side of the wheel, points down. There's a force on this side of the wheel that points down. So it will want to fall down that way. But what if I start to spin this object? If I spin it, there is momentum starting to be formed pointing in all of these directions. So there's this angular momentum being created. In this case, let's see, it's going that way, it's pointing down. Maybe I should hold it like this, so it's easier to show. So we have, I'm going to pull this sort of string that I have wrapped on the base here, and it's going to spin counterclockwise for me looking at it. And the angular momentum is pointing up as it spins around like that. And then if I were to tilt this object over, it's now spinning. At one instant, there is angular momentum pointing outward that way. And in the other instance, so it's going to be going up, still pointing outward that way. So angular momentum is a vector pointing outward. Okay, so there's a vector pointing outward. And there is still gravity trying to force it downward. And if we do this cross product of these two vectors, there's angular momentum pointing outward. There's gravity pointing it downward. Which direction is my thumb pointing? It's pointing that way. So this object, this gyroscope, is going to not be forced down, even though it wants to be forced downward. The angular momentum vector, this cross product, is going to create this oscillation, or this sort of rotation in this gyroscope. So that's what we should expect to see when I do this. Let me make sure I'm holding it right before I might fall, I might mess up, and it might not work. So let's see. So we have this. Also, these are fairly old. I got these a while ago. All right, ready? Oh yeah, it fell off the thing. Okay. In any case, very old. I wish that worked right now. Oh well. There are other videos on gyroscopes. You go take a look. Maybe I'll have it. Maybe I'll have one that works next time. Yeah. So gyroscopes, pretty cool. This was the chapter on angular momentum. I will see you guys later. If you have questions, always let me know. Otherwise, I'll see you tomorrow. All right.